to tackle week 11 and week 12. Actually, the topics are only until week 16, 17, week 17. So, murag hapit na kita mga mano. And, by the way, later, after the discussion, once the majority of you are able to join the class already, um, we would have to agree kung kano sa ta mag-meet for face-to-face because we were required to meet you at least once uh, for the face-to-face class. So it's either we meet on December 9 or December 16. So I will let you decide on that later after the discussion. Okay, so I will now start um, sharing my screen so we can begin. Okay, so is my screen now visible on your end? Okay, so by the way, I will not be able to read your I will just join the other device na lang. Anyways, I cannot join the end because I'm using it for the other class. Okay. So we will be talking, by the way, ang kaning week 11 na material is composed of three things, three topics. We have the water demand, fire demand, and the design flow. So ang pinakaunaan nga part is actually the water demand. Pero we've already discussed water demand, no, during the midterm. So we will skip this one and go directly to the fire demand. So before we begin with the discussion, I just would like to highlight um, or just recap, no, what is water demand. So water demand, especially in water resources engineering, um, this refers to the quantity of water, no, required by the users, no. We have different users of water. We have our households, no, our own houses, in the industries. We have the agriculture for our mga tanom. We need water for firefighting, no, within a specific region or a community. So the water demand is a very critical factor for designing and managing water supply systems. So water demand estimation involves analyzing the current and the future needs of the users, considering factors like population growth, industrial expansion, and climate patterns. So, the accurate assessment of water demand helps us engineers design our infrastructure such as pipelines, reservoirs, and treatment plants. So this is to ensure a reliable and sustainable water supply. So it also plays a vital role in planning and managing water resources efficiently. Also, it could be vital in promoting responsible water use and would help us in addressing challenges posed by increasing demand and potential shortages. So, as we have learned, no, in water demand, we should be able to quantify how much does a community, no, or how much water does a community need. Okay, so for example, we are going to design a pipeline system. So for example, na isang subdivision, we are to design the pipeline system for that subdivision. Now, we should be able to identify or calculate how much does this subdivision need, no, in terms of water. So as we have learned, we have different models, no. The very simple one is the per capita forecast model nga i-estimate niya kung pilay need sa isa ka tao per day, dayon ang kana siya, ang need sa isa ka tao per person, need sa kada person, ihada na siyang i-multiply kung pila ka tao tanan ang mupuyuan nga subdivision. So that is the per capita forecast model. Okay? So we will not dwell much on the water demand. Let us just go directly to the fire demand. Now, what is fire demand? Okay? So, fire demand, especially in water resources engineering, this refers to the amount of water necessary to combat and extinguish fires in a given area. Okay? So it is a crucial consideration in the design and planning of water supply systems to ensure that there is an adequate and reliable water source available for firefighting purposes. Okay? For a while, I will just admit your classmates. Okay. Okay. So before anything else, I would like to apologize if there are unnecessary noise in the background, no, that is beyond my control. Okay, so as I have mentioned earlier, fire demand is the the amount of water, no, approximately needed to extinguish a fire in that given area. Okay, so that means to say, ang katong water demand does not actually include the amount of water that you might need in case of fire. Okay? Ang katong water demand is only solely for consumption per capita. Okay, lahi pod ang fire demand. So, fire demand is typically characterized by by high flow rates and short duration usage during emergencies. So, we need this, we need to identify this as engineers. Um, because we are going to design water distribution systems, including the sizing of water mains and ensuring sufficient water pressure and volume to meet firefighting needs. So, our proper planning for fire demand helps enhance the resilience of a water supply system and ensures the ability to respond effectively to fire incidents, thereby safeguarding public safety and property. So, in general, we need to learn, no, about water and fire demand before we get to the topic where we design for water distribution, because by the end of this subject we will design a pipeline system, no. We are going to identify unsa kadako nga pipe, unsa ka taas, no. We should be able to study water and fire demand first, because or so that we will be able to effectively plan, design, and manage water supply system. So it helps us ensure that infrastructure meets the demands of the communities, industries, and firefighting while considering sustainable resource use and environmental impact. So, our accurate assessment of both the water and the fire demand will help us, no, in sizing of pipelines, storage facilities, and firefighting infrastructure, therefore contributing to the resilience and efficiency of water distribution systems, which we will later on design. Okay, so let us focus on fire demand. So, besides the fluctuation in demand that occur under normal operating conditions, water distribution systems are usually designed to accommodate the large water demands associated with fighting fires. So, although there is no legal requirement that a governing body size its water distribution system to provide fire protection, the governing bodies of most communities provide water for, for fire protection for reasons that um, include protection of the tax base from the destruction by fire, preservation of jobs, preservation of human life, and reduction of human suffering. So, flow rates required to fight fires can significantly exceed the maximum flow rates in the absence of fires, particularly in small water systems. So, in fact, for communities with populations less than 50,000, the need for fire protection is typically the determining factor in sizing water mains, storage facilities, and pumping facilities. So, in contrast to urban water systems, many rural water systems are designed to serve only domestic needs, and fire flow requirements are not considered in the design of these systems. So, numerous methods have been proposed for estimating fire flows, the most popular of which was proposed by the Insurance Services Office. Okay, so I have transferred to another device for the audio. Can you still hear me?
Yes, ma'am.
Yes, ma'am.
Okay, thank you. So, the required fire flow for individual buildings can be estimated using this formula here. So we have capital NFF with subscript I. This is the needed fire flow at the location I. So see here. Okay, I will just zoom in a little bit. Okay. So NFF is the required fire flow. Okay. C here is the construction factor based on the size of the building and its constructions. This is a factor. So most likely this will depend on the type of building, no, and how large your building is. O here is the occupancy factor, reflecting the kinds of materials stored in the building. So usually, the value for this one would range from 0.75 to 1.25. And X plus P here, is the sum of the exposure factor, X, and the communication factor. So these reflect the proximity and exposure of other buildings. So usually the value for this would range from 1 to 1.75. Okay. So we have the CI, no? The CI can be estimated using this equation. So, CI once again is the portion of the fire flow requirement attributed to the size of the building and its construction. No? And we can compute CI, the CI here can be taken or can be solved by this equation. So CI is equal to 220F. So F here is a coefficient based on the class of construction, which is already given. And then the AI or the A here is the floor area. So that means to say, the greater the floor area of the building, the greater the CI will be. And if dako ang CI, mudako po ning NFF. Okay. So this is typically to the equal to the area of the largest floor in the building plus 50% of the area of all other floors. Okay? So that is the A. Okay, mani siya yung estimated. So the NFF calculated using the equation that we have previously flashed should not exceed 45,000 liters per minute, nor it shall not be less than 200 liters per minute. So according to AWA 1992, actually AWA is sa US man no, but we have the fire code of the Philippines. Lahi po to. Okay. So 2,000 liters per minute daw is the minimum amount of water with which any fire can be controlled and suppressed safely and effectively. So 2,000 liters per minute gud ko no ang minimum fire flow. Okay. So, usually, the local water utility will have a policy on the upper limit of the fire protection that it will provide to individual buildings. So, those wanting higher fire flows need to either provide their own system or reduce fire flow requirements by installing sprinkler systems, firewalls, or fire retardant materials. So estimates of the needed fire flow calculated using katong equation kaganiha are used to determine the fire flow requirements of the water supply system, where the needed fire flow is calculated at the several representative locations in the service area, and it is assumed that only one building is on fire at any time. So the design duration of the fire should follow the guidelines stipulated in table 3.6. Okay, we will discuss this one by one. Okay, let us just finish this. Okay, so if these durations cannot be maintained, insurance rates are typically increased accordingly. So we have here table 3.3, if I may zoom in a little bit. Okay, so according to our 1992, so we have classes of construction. No? So basically, um, this refers to what kind of material that you use. Gabi kasaba ang manok. Oh my God. Okay. This refers to what type of materials you use for your buildings. For class of construction, type 1. Okay. Kung frame lang siya, the value for your F is going to be 1.5. Okay. Class of construction 2, which is joisted masonry. Okay? Yeah, the value of your F is going to be equal to 1. So, asa man magamit dire? Okay? So, table 3.4, the occupancy factor. Kani? Oops. By the way, katong F na ganiha. Okay? This is actually the CI here. I know. Yeah. No, the CI is here pala. Yeah, okay. CI is magamit siya og F. So, mao to kaganiha. And then for your OI or your coefficient O, dali mo siya kwaon from table 3 point, oops, table 3.4. Okay? Kung unsa ba siya, if it is a steel or concrete product storage, if it is an apartment, church, or office, or kung department store ba siya or supermarket, kung auditorium ba siya or warehouse, paint shops, or upholstering shops. Okay? Mo din na iyahang value sa O respectively. Okay? So you don't need to solve for the values of these factors. You just have to identify them according to the materials you use for your building, which you can use for your F to compute your CI, and the occupancy factor, meaning unsay purpose ana nga building. Okay? Now, table 3.5, this refers to unsa kalayo ang imuhang building from your neighboring buildings. Okay? So, minimum ni siya kibali. So ang imuhang if imuhang distance between buildings is greater than 30 meters, then the needed fire flow is at least 2,000 liters per minute. Okay? So as you can notice, 9.5 to 30, 3.5 to 9.5, and then less than 3.5. So as you can notice, nga kagamay ang imong distansya sa imong silingan na building, mas magkadako ang imuhang needed fire flow o your NFF. Okay? So katong mga area sa atoa dinhi nga kanang very crowded, kanang mga sikit-sikit og balay, dako na siyang needed fire flow, no, minimum needed fire flow. Okay. So now, table 3.6, this refers to the duration of the fire. So approximate lang, no. So magkadugay, no, ang magkataas ang duration sa fire, 2, 3, 4, 5, 6 hours to 10 hours, magkadako pud ang iyahang required fire flow. Okay, so we have here a sample problem. Okay, so we are to estimate the flow rate and the volume of the water required to provide adequate protection to a 10-story non-combustible building with an effective floor area of 8,000 square meter. So, the equation for the needed fire flow or the NFF, no? Mama ni siya. So, NFF, I'll just rewrite ha, is equal to C or C sub I, O sub I, times X plus P sub I. Okay. So, let us solve for the CI first. So, CI is equal to this one. Okay. So, sa CI, we have two factors, no, that we need the value for. We have the F and the A. And the area is already given, which is equivalent to 8,000 square meter. Now, we need to identify the value of F. But the problem has given us, no, na IQ din he, non-combustible building ko na siya. So, let us go to table 3.3. Non-combustible building, so that means to say, non-combustible na ra siya. Iyang value sa F is 0.8. Okay? It is a non-combustible building, and according to table 3.3, the value for the F is equal to 0.8. So, muna siya tong gamiton dire. Okay, therefore, CI is equal to 220 according to the equation times the F, which is equal to 0.8, times the square root of the effective floor area, which is equivalent to 8,000 square meter. The value for the CI is 16,000 liters per minute. Okay. Okay, so dapat siya, ang bungkig maning ginino, if i-calculator ni maning 220 times 0.8 times the square root of 8,000. Bungkig man siya no namin siya decimal place. But the rule for the CI, it has to be rounded to the nearest 1,000. So if ang value nga makuha ni money is 15,122, you are going to round this off to 16,000. Okay? So may rule. Okay. Now the occupancy factor will be given by table 3.4. Okay. So, in our equation NFF here, we know already the value of the CI, which is 16,000. We still need to get the value for the OI or the occupancy factor. And we can get the occupancy factor from table 3.4. Okay. So, according to table 3.4, for non-combustible building, okay, the value for the O is 0.75. Okay. I will just transfer once again. Okay. So according to table 3.4, the value for the O is 0.75. So let us go back here. Okay. So the O here is 0.75. Okay. And the 16 here is the CI, no, where we were able to identify the value using this equation. Okay. So the X plus P, so X plus P can be estimated by the median value of 1.4. Okay, so hence the needed fire flow will be 16,000, which is the CI, times the OI, 0.75, and the median value for X plus P is 1.4. Okay, so this is also given, ha, the X plus P. Estimated magud siya based on the, what you call this one? Fire demand na forecast. Okay. So the NFF needed fire flow will be equivalent to 17,000 liters per minute. Okay. So this flow must be maintained for a duration of 4 hours. So hence, the required volume of the water shall be, okay, the required fire flow in liters per minute times 4 hours, okay, okay, times the conversion factor, no, 4 minutes, 2 hours, which is 60. So, therefore, the needed fire flow or the needed volume of water or anticipated volume of water nga magasto nimo for the fire demand will be 4,080 cubic meter. Okay. So, any questions regarding this? By the way, this is already available dito sa, what you call this one, Google Drive folder that I have given you. You may, what you call this one, you may review on this already. Okay. Do you have any questions or can you give me a heart react if you were able to understand the topic on fire demand? Okay. Okay, so that was all for fire demand. So moreover, fire hydrants are placed throughout the service area to provide either direct hose connections for firefighting or connections to pumper trucks, also known as fire engines. So a single hose stream is generally taken as 1,000 liters per minute, called the standard fire stream, and hydrants are typically located at street intersections or spaced at 60 to 150 meters. Pero fire hydrants, we rarely see this one in the Philippines, right? So fire hydrants are commonly seen in countries like the United States, mga ano. So in high value districts, additional hydrants may be necessary in the middle of long blocks to supply the required fire flows. Okay? So sa kadako sa volume sa water o sa kakusog sa flow rate nga iyang kailangan, dili siya pwede nga iagi or i-connect ang mga hose, no, didto sa ato ang CR sa lababo. That's why fire hydrants are needed, no? Fire hydrants are installed. Okay. So let us have the design flow. Okay. Pila pa ba ni? Okay. So for the design flow, the typical design capacities for various components of water supply systems are given here at table 3.7. Okay? Typical design period. That means to say, pila ka years? 10, 25, 25 to 50, and ano. So, where low lift pumps refer to low head and high rate units that convey the raw water supply to the treatment facility, and high lift pumps deliver finished water from the treatment facility into the distribution network at suitable pressures. So the required capacities shown in table 3.7, they consist of various combinations of the maximum daily demand, maximum hourly demand, and the fire demand. So typically, the delivery pipelines from the water source to the treatment plant, as well as the treatment plant itself, are designed with a capacity equal to the maximum daily demand. However, because of the high cost of providing treatment, some utilities have trended toward using peak flows averaged over a long period than 1 day to design water treatment plants. So, and relying on system storage to meet peak demands above treatment capacity, this approach has serious water quality implications and should be avoided if possible. So, the flow rates and pressures in the distribution system are analyzed under both the maximum daily plus fire demand plus the maximum hourly demand. So we have here the flow rates and the pressures, no, in the distribution system are both maximum daily demand plus the fire demand and the maximum hourly demand, and the larger flow rate governs the design. So asa sa ilang tuluan ni ang pinakadako, it shall govern, no, in the design. So pumps are based for a variety of conditions from maximum daily to maximum hourly demand depending on their function in the distribution system. So additional reserve capacity is usually installed in water supply systems to allow for redundancy and maintenance requirements. So this is table 3.7. Okay. Okay. So we have here, no, if you are going to if you are going to design a water system wherein ang imuhang um tubig na gamiton is magikan sa river, okay? The design period for that is indefinite. And the design capacity that you are going to govern, no, or you are going to adapt is the maximum daily demand. If it is coming from a well field, you should use the maximum daily demand. If it is coming from a reservoir, you are going to design for the average annual demand. So ana siya, no? So and so on and so forth. Okay, so let us have the sample problem. So a metropolitan area has a population of 130,000, with an average daily demand of 600 liters per day per person. So if the needed fire flow is 20,000 liters per minute, we should be able to estimate first the design capacity for the well field, no, and the water treatment plant, and the duration that the fire flow must be sustained, and the volume of the water that must be kept in service reservoir in case of a fire, and the design capacity of the main supply system, of the distribution system rather. So first, we should be able to identify the design capacity for the well field. Okay. So the design capacity of the well field should be equal to the maximum daily demand. Okay. According to table 3.7. So well field man daw. So money well field. So the design should be based on the maximum daily demand. Okay. So with a demand of with a demand factor of 1.8, so this is coming from the water demand nga topic, ha. So the per capita demand on the maximum day is equal to 1.8 times 600. Okay? So that would be equal to per capita, that is 1,080 liters per day per person. Since the population is served 130,000, The design capacity of the well field is given 1,080 liters per day per person times 130,000 person. So that would be equal to 1.4 times 10 to the eighth liters per day. Or that is 1.62 cubic meter per day or cubic meter per second rather. So the design capacity of the water treatment plant is also equal to the maximum daily demand and therefore should be taken as 1.62 cubic meters per second. Kaya i-base man daw siya sa maximum daily demand according to table 3.7. Now, the second being asked from us is the needed fire flow. Okay? Ano? So to, ikaduha? The duration rather. The duration that the fire flow must be sustained and the volume of water that must be kept. Okay. So, the needed fire flow is given no, in the problem, which is equivalent to 20,000 liters per minute, or that is equivalent to 0.33 cubic meters per second. So, according to table 3.6, the fire flow must be sustained for 5 hours. So, ato to table 3.6. Okay, ni remember this one. 20 liters per minute. Let us go to table 3.6. Here. Okay. So, based here, how much was it? 20, no? So, it falls here. Nasya din eh. So, it should be maintained for 5 hours. Okay? So, 5 hours ko, no? Ngayon, ana ako kusog ang flow rate, which is 20,000 liters per minute. Okay? Going back here, 0.33 cubic meter per second, no? This is just a conversion of the 20,000 liters, ha? Times 5 hours, okay? Times, kakanin 36, then this is the conversion factor of seconds to hour. Okay? Kay, this is 0.33 cubic meter per second times 5 hours man. So for us to be able to cancel out the hours, we have to convert it into seconds. Then after that, we are going to be left with the cubic meter na yun, which is equivalent to 5,940 hours. So the answer to how long shall the fire be sustained, the fire flow be maintained is equivalent to 5 hours, and the volume that is required no to be stored in the service reservoir in the case of fire is 5,940 cubic meter. Okay. So now, mo to siya ang ikaduhang gipangutanan. The last is we should be able to identify the design capacity of the main supply pipeline to the distribution system. Now, the required flow rate in the main supply pipeline is equal to the maximum daily demand plus the fire demand or the maximum hourly demand, whichever is greater. Okay? So, ang first option nimo, we have to check maximum daily demand plus the fire demand. Second would be the maximum hourly demand. Okay? Okay. So, the maximum daily demand is 1.62. Okay, based na ni sa atong answer sa A. Plus the fire demand which is given to be 0.33. So 1.62 the maximum daily demand, okay, which we have which we have computed based on the per capita consumption plus 0.33 rather, which was given already. So that is equivalent to 1.95 cubic meters per second. Okay. So the maximum hourly demand is equal to 3.25 over 1.8 times 1.62. So this 3.25 here has been assumed for the maximum hourly demand. So this is assumed kaning 3.25 here. So the main supply pipe to distribute water should be therefore designed to a capacity of 2.92 cubic meters per second. So The maximum hourly demand is 2.92. The maximum daily demand plus the fire demand is equal to 1.95 lang. And according to um our discussion, the one greater should govern. Therefore, the 2.92 cubic meter per second shall be the system demand, no, to be adapted in the water distribution system. Okay, so 2.92 should be your design flow rate for your water distribution system. Okay, so ana lang siya. Do you have, okay, that ends our discussion. Do you have any questions and clarifications? Okay. Can you give me a heart react if you were able to understand the discussion this morning? Okay. So now, can we agree kanus ata mag face to face? What would you suggest? December 9 or would you prefer December